Welcome everyone! Today we'll be talking about
indicators!
Indicators are complex organic molecules that are weak acids or bases that change color when pH changes. They are used in titration to help determine when titration is complete.
This is an acid-base indicator table. For phenolphthalein, solutions less than pH 8.2 will be colorless, and solutions greater than pH 10 will be pink.
Here are some ways to determine if something is acidic or basic.
The pH meter is used to determine accurate pH but takes time to calibrate. It also requires several milliliters of test solution to work.
There are also universal indicators such as litmus or pH strips. These turn red in acids, green in neutral solutions, and blue in bases.
Lastly, when magnesium is added into acidic solutions, hydrogen gas will be given off.
There are also natural indicators, which we'll discuss later on.
Indicators are represented by abbreviations. IN or IND means indicator. The conjugate acids are represented by HIN or HIND, and the conjugate bases are represented by IN negative or IND negative.
Indicators change color over a range of pH, not an exact pH. Also, the conjugate acid and base forms have different colors. In addition, weak acids or bases form equilibriums, like the equation shown below.
If we add an acid, there will be an excess of H3O plus at equivalence point. This means that if an acid is added, the concentration of H3O plus will increase. To counteract the stress, the equilibrium will shift left towards the acid form of the indicator. Correspondingly, the concentration of HIND will increase and the concentration of IND minus will decrease. In conclusion, the concentration of the acid form will be greater than the concentration of the base form.
By Le Chatelier's principle, the solution changes to the color of HIND, which is yellow. As a reminder, don't forget the solution is orange due to the equal amount of acid and base, which is yellow and red, which turns into orange. In conclusion, in highly acidic solutions, an indicator will be in its conjugate acid form.
If we add a base, there will be an excess of the hydroxide ion at equivalence point. This means that when a base is added, the concentration of H3O plus will decrease as the hydroxide ion reacts to neutralize the hydronium ion and forms water. To counteract the stress, the equilibrium shifts right towards the base form of the indicator. Accordingly, the concentration of the acid form will decrease and the concentration of the base form will increase. As a result, the concentration of the base form is greater than that of the acid form.
By Le Chatelier's principle, the solution changes color to the base form, which is red. In conclusion, in highly basic solutions, an indicator will be in its conjugate base form.
Some indicators change colors more than once. For example, Thymoblue has two color changes. It turns from red to yellow from pH 1.2 to 2.8, and from yellow to blue from pH of 8.0 to 9.6. This tells us that the indicator is a diprotic weak acid. When a base is added to an acidic solution, eventually the concentration of HIND will equal to the concentration of IND negative. In this previous example, an equal number of yellow and red molecules will result in an orange solution, and this point halfway through the color change is called the endpoint. Selena is a solution going through a midlife crisis. She knows she changes color around her acidic and basic friends, but she doesn't know which color she'll turn with each group. Therefore, she is having trouble deciding what type of friend she wants to have. Here comes Kaylin and Winnie, the indicator fairies, to the rescue. First, as Selena's concentration of H3O plus and OH negative is equal, the indicator fairies indicate that she is neutral, showing that she has equal concentrations of the acid and base forms of the indicator. At this moment, she is orange. When she has an excess of the hydroxide ion, they indicate to her that she will turn red with a greater concentration of the base form than the acid form of the indicator. When she has an excess of H3O+, they show her that she will turn yellow with a greater concentration of the acid form than the base form of the indicator. From now on, Selena knows that hanging out with basic friends, she will turn red. When she's with acidic friends, she will turn yellow. Who will she choose? At the end, Selena chooses to have a balanced life and to simply stay neutral, either being alone or to hang out with everyone. She wants to stay orange with an equal concentration of acid and base forms of the indicator. Selena's issues are resolved! Yay! Now let's do some calculations. The endpoint of an indicator means the same thing as a transition point. At this point, the concentration of HIND is equal to that of IND negative. Using these ideas with our Ka equation and knowing that the concentration of the acid and base forms of the indicator are equal, therefore cancel each other out, we are left with Ka is equal to H3O+. If we take the negative log of both sides, we will get pKa of the indicator is equal to the pH of the solution. However, please note that this is only true at endpoint. Taking brown creosote green as an example, if we take the average of the two pH values in its pH range, we will get 4.6. To solve for Ka, we will need to calculate 10 to the power of negative pH. By plugging in a pH of 4.6, we will get a Ka of 3 times 10 to the negative 5. Indicators help determine equivalence point visually and allow us to see when stoichiometry of the reaction is achieved. An appropriate indicator changes color very close to the equivalence point. So to choose the best indicator, choose one whose endpoint is closest to the equivalence point of the titration.
Universal indicators are mixtures of many indicators with several color changes over a large pH range. They are used when the pH of a solution is unknown and for approximating pH of unknown solutions within 0.5 pH unit.
Now let's talk about some natural indicators. They can be prepared in many different ways, such as being pureed, submerged in boiling water, or powdered substances can be mixed with isopropyl alcohol. Curry or turmeric solution is a common natural indicator. These substances contain the pigment curcumin, which normally changes color from yellow at pH of 7.4 to red at pH 8.6. Turmeric is also found on many paper indicators.
This is what curry solution looks like when it is added into acidic and basic solutions. As you can see, it turns yellow in acidic solutions and orange-red in basic solutions.
Red onion extract can also be used as a natural indicator. It is purple in color because it is rich in the pigment anthocyanin. It changes from pink in acidic solutions to green in basic solutions.
Although the colors in this picture is hard to see, it demonstrates how red onion extract turns pink in acidic solutions and green in basic solutions.
Strawberry extract also contains anthocyanin. This gives strawberries a red color pigment. Strawberry extract will turn darker in red in acidic solutions.
As an example, we can see this picture shows how strawberry extract turns from a darker pink in acidic solutions to a lighter pink in basic solutions.
Black tea is another example of a natural indicator. It contains large amounts of thiorubigen, which is responsible for its color pigment. This is why black tea turns to a lighter color in acidic solutions like lemon and tea, and turns darker in basic solutions.
Although the quality of this picture is not that good, we can see here black tea in acidic solutions turn into a lighter brown color to a darker brown color in basic solutions.
Grape juice also contains anthocyanin. This pigment gives grape juice its purple tint. This natural indicator turns red in acidic substances.
If you look closely at this picture, you can see how grape juice in acidic solution is pink and turns colorless in basic solution.
Flower extracts are one of the most common natural indicators. For example, morning glories and petunias, which contain a pigment called anthocyanin, turn purple-red in acidic solutions and blue-violet in basic solutions. Hydrangea flowers also contain anthocyanin, but they turn pink in acidic solutions and red in basic solutions. Some other types of flowers, such as delphiniums and geraniums, contain anthocyanin pelargonin. This pigment allows the natural indicator to turn orange-red in acidic solutions and blue in basic solutions. Lastly, the oxyminium salt of cyanin in rose petals change from red to blue in basic solutions. With the help of these flowers and the concepts of indicators, gardeners can see if their soil is acidic or basic.
Thanks for watching!